Hello there, welcome to Lab Observations, Motion of the Night Sky around Polaris, the North Star. This is all in Pivot Interactives. So welcome to Pivot Interactives. Here's how it all works. Okay, we have learning objectives. Our learning objectives in this case is to introduce the system to you and also measure the apparent motion of stars in the night sky, and that includes planets, all the constellations around a point in the sky. So Pivot Interactives uses video footage that we can control and analyze. So in this case, we have time-lapse video of stars on a winter night. This was recorded in Ely, Minnesota in 2013 at a latitude of 48 degrees north. Okay, there are lights that flicker on occasionally. What we'll see is we don't see the critter, but there's probably some wildlife out there that triggers a light around the cabin from time to time, but it doesn't affect our measurements. Okay, so here's the video. We have general controls, reset, forward, backwards, and play, and also a scroll bar over here that you can grab with your mouse, or if you're doing this on a touch screen, you can do that with your finger as well. All right, so here's what we're going to do. We're going to first expand this so we can see it best. So we will go full screen. That's down here. So I'll hit the expansion button, and we're at full screen. What we have here is a starscape. Now, if I hit play, what we'll see is that it appears the stars rotate in the sky. And there are those flashes I was referring to, the lights turning on, perhaps little critters. And here, one frame, a frame is a picture that's taken, is done every minute. So every minute goes by and there's a picture taken. And then later on, it's every 5 seconds. So they do change it just to see what goes on. In this case, what we see are these satellites that streak across the sky. So that is in view there. And perhaps we can even measure, there are ways to measure that too, although we don't have the tools for that this time. So what we're going to concentrate on is what we can do. And that's measuring the angular speed, degrees per second, degrees per minute, of the rotation. And the tools that we want to access are always in the top right corner of the Pivot Interactives video. So I'm going to click on that. And what we have is an option for one tool. Sometimes there are more. Sometimes they're going to be rulers, timers, protractors, of the like. In this case here, we have a circle that can measure degrees all around that circle. So it's a circular kind of a compass that measures in degrees, and this is the tool we'll use in this investigation. So what we can do is this. We'll go look at our questions to give us a guide here. Use measurements from the video to determine the angular speed of the stars in degrees per second. So we can do degrees per minute, but degrees per second is specified. And one of the hints here is to not use Polaris, the North Star, to measure because it's too close to the center of the protractor to be able to make the accurate measurements. Okay, so we'll note that. So Polaris is this guy over here. When we play, we'll notice that Polaris is relatively fixed. It doesn't move a whole lot. You can generally use Polaris in the night sky as your northern beacon. It is a star that points perfectly north, and it stays almost fixed in the sky. It's obviously varying just a little bit here. We don't want to use Polaris because it's very close to center. So what we really want to do with the frame per minute cycle here is choose a star on the outside that we can measure and track all the way around. So the amount that you choose is up to you. Obviously the lines are marked every 30 degrees. It would be better if you can get more than that and then extrapolate it all the way to 360 degrees. So maybe we measure instead of 30 degrees, it could be 120 degrees or 150 degrees, somewhere in there that we get a decent measurement. We'll figure out the time by looking at the frames. Each frame represents a minute, and it tells you which frame you're on. So in this case, we're starting here at frame 150. If we go forwards, we get frame 296. And we would track the stars and figure it out that way. So move this around accordingly to make your measurement and figure out how much time it takes to move a certain angle. From there, we can extrapolate and figure out what it takes to make one revolution, which is 360 degrees. Okay, so let's further look. Now, your responses will go directly into Pivot Interactives. So when this assignment is graded, I will do that from Pivot Interactives and then move it in to Blackboard Learn later. I'll move the grade in later. So number 2 says to use measurements in the video to then determine the period. Okay, so how much time then would it take for a star to move all the way around one revolution? And you can express that in seconds and hours, various units. Lastly is a question that asks, why do you think that all the stars appear to have the same angular speed and period of rotation? What could cause them to appear together in unison? So this relates to some of the other topics that are part of our unit on observations and measurement, and that would be, well, the Flat Earth Society and those fellows who are the contrarians. There's been evidence for over 2,000 years set up by the ancient Greeks that have determined that the Earth is spherical, and there's evidence to support that. This is another piece of evidence, perhaps, that can justify another aspect of the same phenomena. So sometimes disparate measurements of different phenomena actually lead to conclusions about the same thing. It's just reinforcement, more evidence to support the various conclusions. So that's our introduction here to Pivot Interactives. We'll be using it a lot in more sophisticated manners with longer labs. This is just the first one that we're going to do. So I hope you enjoy the experience. If you have questions, obviously, post them on the discussion forum, or you can still contact me via email as well. All right. Thank you much for watching. This is Morad, out.